All right, let's start talking about ellipses. Let's look at your packet that you have and talk about what an ellipse is. Essentially, you can think of an ellipse as an oval. That's your previous experience. We're going to look at ellipses in this handout that are in standard form. General form we'll pick up in another day. Several things to know about an ellipse. An ellipse can be horizontally oriented, meaning it's like an egg, so to speak, laying on the table, or a football waiting to be hiked. Or perhaps that ellipse could be vertically oriented, meaning it's an egg sitting in its egg carton. So it's oriented one way or the other. There's several things we need to know about an ellipse. As you look at this graph, there's several things labeled. We need to know a center. There are 4 vertices. We need to know how to calculate all 4 vertices. There are 2 foci, which is plural of focus. Parabola only has 1 focus. There are 2 for an ellipse. Plural of focus is foci. We have 2 axes of symmetry. One that is longer and one that is shorter. Longer axis of symmetry is called the major axis of symmetry. Shorter one is called the minor axis of symmetry. And what you see before here is semi-major, which means that's halfway across the axis of symmetry. From the center to a vertex, that's semi-major. From this center to that vertex, that would be the semi-minor. It's halfway across that way. What does an ellipse look like in standard form? Well, here's what the equation looks like. X minus h quantity squared over a squared plus y minus k quantity squared over b squared equals 1. It must always equal 1. If it's not 1, you've got to make it equal 1. Now, question is, how do we know whether it's horizontal or vertical? And to answer that question, look at the denominators. A squared is greater than b squared. The key to finding out whether this is horizontal or vertical is to look to see which denominator is larger. That is only true for ellipses, not true for hyperbolas. So please keep that in mind. So if the larger denominator is under x, the x-axis goes left and right. Our oval shape is going to be stretched more to the left and the right. So that's what we want to look at. The larger denominator is what we're looking for. If that's under the x term, that's horizontal. Center we can find just pretty much like we did for a circle. Opposite of what's in parentheses with x, that's h, the x value of the center. Opposite of what's in parentheses with y, k, that's the y value of the center. An ellipse has a center just like a circle does. Now, we just momentarily talked about the axes of symmetry. There's a major axis, that's the long one. A, the square root of the largest denominator, is half the length. It's the length of the semi-major axis. It's half the length across the major axis of symmetry. B, the square root of the smaller denominator, that's going to be the length of halfway across the minor axes. If we look for a moment at the picture again, you'll see that the vertices are located where the major axis of symmetry intersects the ellipse, and where the minor axis of symmetry intersects the ellipse. There are 4 vertices. So we can use A, the distance from the center left and right, to find 2 of the vertices. We can use B, the distance from the center to each of the other 2 vertices. And if it's horizontally, what we need to do is we need to take that A, add it to the x value of the center, subtract it from the x value of the center, and that's how we find 2 of the 4 vertices. Those are the 2 vertices on the major axis of symmetry. B, for a horizontal ellipse, we're going to go up and down from the center to find the other 2 vertices. So we're going to add that B to the y value of the center, subtract that B from the y value of the center. That's how we can combine and calculate the vertices without even drawing them on the graph paper. I will be asking you to do that. We also, if we look at the graph momentarily, have something called C, and that represents the distance from the center to each focus. So the letter C represents the distance from the center to each focus. How we calculate c is the square root of a squared minus b squared. Let's remember what a squared and b squared represent. A squared is the largest denominator, b squared is the smallest denominator. So essentially we're saying the distance from the center to each focus is large denominator minus small denominator. We subtract them, then we square root them. And to calculate where those two foci are located, what we need to do then is to add or subtract that, because C is always going to go the direction that A goes. Our foci are always on our major axis. A describes our major axis. So what we're going to do is we're going to take that C and we're going to add it and subtract it to and from the center, the x value of the center, and that'll tell us how to calculate the focus. So add that C to the x value of the center, h, subtract that C from the x value of the center, h. That'll tell us the coordinate points for those two foci. All right, eccentricity for an ellipse is calculated. We use the letter E to represent eccentricity. Is calculated by taking this C, the distance from the center to each focus, divided by A, which remember was the square root of the large denominator. And here's a way to check to see if you've calculated correctly. For an ellipse, E should be greater than 0 and less than 1. Not including 0 because that was a circle. Not including 1 because that was a parabola. So eccentricity for an ellipse should always be greater than 0, less than 1 when you calculate C, distance from the center to each focus, divided by A, distance from the center or the half of the semi-major axis. All right, let's take a look at vertical. Vertical, there's very much similarities. And again, let me bring your attention to the fact that A squared is larger than B squared. So it makes this equation the equation of a vertical ellipse is this fact right here that a squared, the largest denominator, is under y. If the larger denominator is under y, y-axis goes up and down, your ellipse should be stretched up and down. The center is still HK. A is still the length of the semi-major axis. And that's still the square root of the large denominator. It's just where you find the large denominator that's different. B is still the length of the semi-minor axis. That's the square root of the smaller denominator. Vertices are still found in this fashion, so we're going to start with the vertices going up and down on the major axis. And we're going to add A and subtract A to and from the y value of the center. And then B, we're going to add that to the x value of the center and subtract that from the x value of the center. It's just that A and B are going to go in different directions. C is still the distance from the center to each focus. The way we calculate C is still the same. C is the square root of the large denominator minus the small denominator. To calculate those foci, the foci are always on the major axis. Since the major axis is going up and down, I'm going to add C to K, the y value of the center, subtract C from K, the y value of the center. And again, it's still an ellipse, so eccentricity is calculated as E equals C, the distance from the center to each focus, divided by A, the square root of the large denominator. And to check that you're in the right ballpark here, the right neighborhood, that eccentricity should be greater than 0 and less than 1. So that's the look at the formula sheets. You can see as we look at this vertical ellipse, we're going up and down A, left and right B. Our foci are still on the major axes. And the four vertices are still where the two axes of symmetry intersect the ellipse. So that's the formulas for an ellipse.